Okay, so final minus initial, okay, and then all we have to do is go m times g times h final minus m times g times h initial. In this situation, what's my initial height?
0.
So what's my initial potential energy? 0. Okay, so all I have to do is that then, yeah? Okay, so that's pretty straightforward. 500 kilograms times 9.81 times 48 meters. Okay, and we've got our change in gravitational potential energy. Right? We were doing stuff like that with our questions the other day on work energy theorem, so it's nothing new. Okay, just reiterating it here for you. Okay. Now, this question is very similar, okay, but it's illustrating the importance of a reference point. Okay? Most of the time, when we're dealing with gravitational potential energy, our reference point is the ground, height of 0. Okay? But occasionally, you'll get a question that uses a different reference point. Like, let's say you're in an office building and you're on the 2nd floor and you have to take a package to the 10th floor. What's its change in gravitational potential energy? Well, I'm only carrying it from the 2nd floor to the 10th floor. I only change its potential energy between those 2 points. But somebody had to bring it to the 2nd floor. If the question doesn't tell me otherwise, I assume I start on the 2nd floor, not the ground. Now, if the question says, with reference to the ground, then I know I've got to figure out how far it is from the 2nd floor to the ground and put that number in as well. Okay? So it's always important when you're reading a question to see, do they say something like this? Relative to the floor. Because in this question, the car starts up top here and ends on the table. It never gets to the floor. Okay? But the question wants to know with reference to the floor. Okay? So I have to make sure I calculate it that way. All right? So calculate it that way. Okay, so let's have a quick look at this one here, guys, because we're just looking for the change in gravitational potential energy of the car. Okay? So if I do this, okay, I can find, if I want to find change in potential energy, right, then I just go m times g times h final minus m times g times h initial. All right? Now, is my change going to be negative here? It is, because I'm lower at the end than I am at the beginning. I actually lose potential energy. It's okay if my number comes out negative here. All right? Now, what I would do here is take the mass, so 0.025 times 9.81 times 2.15 meters, okay, my height from the ground, and I would, sorry, other way, 0.950 meters, that's the final height, minus 0.025 times 9.81 times 2.15.
And what does relative to the floor do?
What's that?
Because when it says relative to the floor, can you just explain that again, and what that means?
That means I'm using the heights as measured from the floor. I'm not saying this height minus this height.
Okay.
Okay? Like I'm not saying that this is 0 and this is 30 centimeters higher or 20 centimeters higher. Yeah? I'm always measuring from the floor.
Okay.
Okay? So if I do that, okay, so I got 0.025 times 9.81 times 0.95 minus 0.025 times 9.81 times 2.15. Whoops, I got a minus in there. Hang on. I made a mistake. That's supposed to be multiplied. Okay, so I get negative 0.2943 joules. Okay, is that all right? Yeah, my energy decreased. Is there a way I could have done that that's shorter? Since both of these start with mg, could I have just done this? I could have. Okay, so that would have been 0.3 meters, and I would have got exactly the same number. Okay, so if I go 0.025 times 9.81 times 0.3, or sorry, it's 0.2 meters, sorry, right? Yeah, No. 0.25 meters. Yeah? No. 0.2 meters. I'm going crazy. 0.2 meters.
Do you want me to do it?
Oh, yeah. You know what? Sorry, you're right. I'm just gonna do this, 2.15. I'm struggling with the math today, guys, sorry. My coffee ran out hours ago.
1.2.
1.2. Okay, but look, I get the same number here, right? 0.2943, okay? That only works for potential energy. Don't think you can do that with kinetic where the number is squared, okay? It doesn't work the same way when it's squared, right? All right, questions on how that one works? Okay, so just the importance of that was a reference point. Obviously, you know how to do m times g times h already. Okay, just if it tells you relative to this point or if it tells you relative to the ground, just make sure you're paying attention to that. Okay, that is important for question number 1 about the pile driver. Okay, so it says here a pile driver drops a mass of 550 kilograms from a height of 12.5 meters above the ground onto the top of a pile that is 2.30 meters above the ground. Okay, relative to ground level, what is the gravitational potential energy of the mass at its highest point, at its lowest point, and what is the change? So it's exactly the same as the last question we did, except now it's a pile driver.
And there's no picture.
And then there's no picture. Okay, so in case you don't know, this is a pile driver. It's a tool, not a wrestling move. Okay, now with a pile driver, all it is a big mass, and they just lift it up with a crane, and then they drop it onto essentially like a stick. Okay, it's usually made out of metal or concrete. Okay, and they pound these pilings down into the ground by dropping. It's a big hammer, basically. Okay, we want to put pilings in the ground, especially in areas like this, because we want whatever the building is sitting on to be below the frost line. That way, when the ground freezes, the building doesn't heave because the ground expands. If what it's sitting on is below that, then its height won't change when the ground does weird things in the winter and in the spring. Okay, so you have to put everything on a piling. If you've ever built like a deck or something on your house, you have to put pilings in the ground so that it's stable, and that's building code, right? So that's what we're dealing with here, is just something that pounds those pilings down into the ground. Okay, big hammer, right? Which oddly enough does look a lot like the wrestling move where you pick somebody up, turn them upside down, and drop them on their head. Okay, kind of looks like that. Okay, give you a minute, give that one a try. Okay, so for this one here, for part A, what's its potential energy relative to the ground at its highest point? So EP is m times g times h, so that's going to be 550 kilograms times 9.81 times 12.5 meters. Okay, that gives us our energy at its highest point. Okay, we want to calculate the energy at its lowest point. Same calculation, except instead of 12.5, I use 2.3 because that's its lowest point, 2.3 meters. Right? And then to find the change, I just do what with those? Subtract them. Everybody all right with that? Pretty straightforward. Like I said, we did much harder questions than that yesterday. This is basically just reviewing, okay, what you know. Yep. All right, when we're talking about kinetic energy, okay, 2 things affect kinetic energy. What are they? Mass and speed, yeah. So how fast it's going and mass. Which one affects it more? Velocity or speed. Okay, because in this formula, speed is squared. Okay, that means any change in speed results in an exponential change in the kinetic energy. Okay, if I've got 2 objects, okay, both going 5 meters per second, but one is 100 kilograms and the other is 200 kilograms, the 200 kilogram mass has twice as much energy. That is not true with speed. If I have 2 100 kilogram masses, one moving at 20 meters per second, one moving at 40 meters per second, the one moving at 40 meters per second has not twice as much, 4 times as much energy, because the effective speed is exponential. Okay, everyone follow me there. It's really important for us to remember that, okay? Speed has an exponential effect on kinetic energy and thus the ability of something to do work. Okay, think of it this way. If somebody picks up a bullet and throws it at you, are you really worried about it? Can it really severely hurt you? No, because probably the fastest they could throw it would be about 30 meters per second. Okay, it might hurt, but it wouldn't hurt you severely. Okay, that same bullet, if fired from a gun, could be moving 900 meters per second. Okay, that's not 30 times more energy, it's 900 times more energy because the effect is squared. Okay, everybody follow me there? Okay, so it's a big deal, right? Okay, all right. So, got to understand that part there. Okay, obviously mass has a linear effect. Okay, so more mass means more energy, but only linearly. If I double the mass, I have double the energy. Okay, so important for us to recognize that. Okay, so here's a question that kind of demonstrates that a bit. These two vehicles have the same kinetic energy. One of the vehicles is 1,200 kilograms, moving at 20 meters per second. The other is a big loaded van, and its mass is 4,800 kilograms. In other words, 4 times the mass of the first vehicle. They have the same kinetic energy. How fast is the van going? See if you can calculate it. Okay, they have the same kinetic energy. Okay, but the van is 4 times heavier than the car. How fast does the van go? Okay, so by the same notion, if something 4 times as fast, or sorry, 4 times as heavy, goes half as fast to have the same amount of energy, okay? Nope, not that one. Think about this cannon question. Okay, first cannon fires a 1.5 kilogram cannonball at 550 meters per second. A second cannon fires cannonballs with 1/3 the mass, but double the muzzle velocity. Okay, so smaller cannonball by 3 times, but twice the speed. Which one is better at damaging a fortification? Okay, because back in the day, that's how warfare worked. Okay, you had a cannon, you put a big metal ball in it, okay, and you launched the metal ball at the opposing person's castle, right? The more kinetic energy the ball had, the more damage that you could do. So what's better? A heavy ball, okay, moving at 550 meters per second, or a lighter ball, 1/3 the mass, moving at twice the velocity? I'll give you a few minutes. Maybe you want to calculate it, maybe you don't, maybe you figure it out in your head, okay? But I'll give you a few minutes on that. Okay, in the last question with the van and the car had the same kinetic energy. The van was moving half as fast as the car, but was 4 times as heavy. In this question, the first cannon is 3 times heavier, but moves at half the speed. So, which cannon is better? The smaller one. The smaller ball has more kinetic energy because it's speed that makes the bigger difference. Okay? If I had reduced that to 1/4, then they'd be equal. Okay? If I had said that the second cannon fires cannonballs that are 1/4 the mass of the first at twice the speed, it wouldn't make any difference. It'd be a coin toss. I could fire either cannon, they'd have the same. But because I only reduced the mass by down to a factor of 3 instead of 4, the second cannon still ends up with more kinetic energy because speed has a greater effect. By doubling the speed, I give the cannonball 4 times as much energy. And then I reduce its mass by a factor of 3. Well, that's still bigger than the first cannon. It's like 4/3 instead of 1/1. Okay, like the first cannon we would say was 1/1. The second cannon has 4 times more energy because of the speed, but 3 times less energy because of the mass. Well, 4 over 3 is still greater than 1. So as a result, the second cannon has more energy. Okay? This is the principle behind all kinetic based weapons. Okay, I don't know if anyone's heard of this, kind of a science fiction thing, but anyone's heard of a railgun? Okay? A railgun is theoretically going to work by firing a projectile at nearly the speed of light. Okay? The projectile then doesn't have to be very big to have a great deal of energy. Okay? So basically it just fires a depleted uranium slug. Okay? So just a chunk of depleted uranium. Okay? But it fires it at an incredibly high rate of speed. Which means if you have, let's say, a naval vessel, a warship, that's not carrying explosive ordnance, it's only carrying kinetic ordnance, you're way safer on that boat. Because what will that boat not do? Right, if you get hit by your opponent and they're launching explosive stuff, your own ordnance doesn't blow up. Okay, that's what sinks most ships, is their own weapons blowing up when they get hit by the other person's weapons. If you have a ship that's only carrying big, heavy masses that they're going to launch at you at an incredible rate of speed, you don't have to worry about your own ammo blowing up. Okay? And you've got these big slugs that can go really, really fast and just punch holes in other ships because they're moving so fast. Okay? They don't even have to blow up. They're just going so fast, they just poke holes in everything. Okay? Does that sort of make sense? That's the idea behind kinetic energy weapons. They don't actually have to have explosive ability. Okay? So, that brings us to question number 3. When meteors strike the Earth, they do a lot of damage. They make big holes, like this one. Okay? That's Barringer crater or meteor crater in Arizona. It's about 1,300 meters across. Okay? It was produced by a meteor 40 meters across. Okay? So the meteor wasn't very big compared to the hole that it made. All right? So what caused most of the damage? The mass of the meteor or the speed? Speed. Yeah. Okay? It has a lot of kinetic energy. So I'd like you to try question number 3. The first part is just calculating the kinetic energy of the meteor. Okay? There's only one trick to that. They give you the speed of the meteor in kilometers per hour. Okay? You need it in meters per second. The second part is how we measure the damage of things. We measure the damage or the damage potential of things in tons of TNT. So basically, if I detonated this many tons of dynamite, it would do the same amount of damage as that thing. Okay? So that's why we measure everything in tons of TNT. So I want you to figure out how many tons of TNT would be needed to make that hole. So for part A, we need to calculate the kinetic energy of the meteor. So first thing we need to do is convert this 72,000 kilometers per hour to meters per second, which means we divide by 3.6. So 72,000 divided by 3.6 gives us 20,000 meters per second. Okay, so now I can plug in and calculate the kinetic energy. So I take that 1/2 times 2.6 times 10 to the 8 kilograms, the mass of the meteor, times 20,000 squared, okay, and I'll get this big number. Okay, 5.2 times 10 to the 16 joules. Does that sound like a lot? It's because it is a lot. Okay? Now, in part B, it tells us that 1 ton of TNT releases 4.6 times 10 to the 9 joules of energy. Okay, so if I piled a bunch of crates full of dynamite until I had 1,000 kilograms of it, okay, that's how much energy it would release if I blew it all up at the same time in a Minecraft-esque way. Okay, so if I take this number and divide it by the amount of energy available in 1 ton, I will get how many tons of TNT were needed to make that hole. Okay, so 4.6E9, okay, so I'm dividing by that. 11.3 million tons. That makes that meteor an 11.3 megaton detonation. Okay? The bomb dropped on Hiroshima was 20 kilotons. That's 20,000 tons. This was 11.3 million tons. Okay? To give you an idea, the average nuclear weapon today is around 1 megaton. The largest ever detonated was 57 megatons. 57 million tons of TNT. Tsar Bomba. Okay, it was dropped by the Soviet Union on their own soil to test it. Aren't you glad you didn't live there? Okay, yeah. It destroyed houses hundreds of miles away.
Did they drop it on people? Is that what you're saying?
No, they dropped it in an area that was completely uninhabited in Siberia. They just had no idea how big the explosion was going to be, which is now why above ground nuclear testing is forbidden.
Did they have like a timer for it, so they had to like drop it and run?
Yeah, the people in the, no, not run. They dropped it right.
And it's flat.
Yeah.
So did they die?
Nope, but they felt it. Yeah.
When was
Kind of
this-
scary.
When did this meteor hit?
This meteor, thousands of years ago.
Oh, okay, I was gonna say, 'cause I was like, Arizona would stand a chance.
Well, I mean, it's a big hole. It's 1.3 kilometers across.
I thought it was
And,
like, have, like, a
and that's only 20,000,
You have like a date.
or that's 11.3 million tons. That's a lot. You drop that on the city.
Yo.
No, it's pretty much gone. All right, making some sense?
And then
Or you
you
can
can
rock
take it
yourself
away.
to sleep tonight with that thought, okay? There are hundreds of nuclear warheads. Each one of them is 1 million tons of TNT.
Do you want to know how 50-50%?
Yeah, exactly. Yeah, it wasn't pleasant. Okay, guys, I got a couple questions here I'd like you guys to try. Yeah, they had no idea how much. Okay, I want you guys to try number 7 here, guys. So there's 2 ways to do this one, okay? If I'm changing the kinetic energy, okay, what kind of a force changes kinetic energy? What kind of force makes something's speed change?
Acceleration.
What kind of force creates an acceleration? F net. Okay, so can I calculate the net force in this question? I can. I've got mass and acceleration, right? Well, actually, I don't have mass, but I can get it. And actually, no matter which way I do this question, the first thing I have to calculate is the mass. So I've got to take the force of gravity, 10 newtons, and divide it by 9.81. Right? So that's the first step, regardless of which way I do this. Okay, so 10 divided by 9.81 is going to give me 1.02 kilograms worth of mass. Okay, so method 1, I can calculate the net force because I now have mass and acceleration. Everyone okay with that? Okay, so F net equals m times a, so that'll be 1.02 times 2.5 meters per second. All right, so there's my net force, 2.55 newtons. Okay, net forces cause accelerations, which means net forces cause changes in kinetic energy. Agreed? Okay, so net forces do work. And work is a change in energy, in this case, kinetic energy. If I do this, will I get the final kinetic energy of the object? Since it starts with nothing, right? It specifically states it starts from rest in the question. Okay? If I take F net and multiply it by the distance, which they also gave me, I'll have 38 joules. Okay, 2.55 times 15. .38 joules. Okay, so that's one way to do this, right? I had to calculate the mass, which I'd have to do regardless of the method. I calculated net force, and then I used net force when I went work is force times distance. Okay, 38 joules. Work is also a change in kinetic energy, would you agree? How much kinetic energy does this thing have initially? 0. So would its final kinetic energy also be my answer?
Yes.
Okay, so if I just go like this, EK equals 1/2 mv squared, I should get 38 joules, yes? Problem is I don't have V. Can I calculate what V is? Yes, because I have VI, A, and D. So if I go VF equals the square root of VI squared plus 2AD, I'll have VF. So square root of 2 times my acceleration, which was 2.5. Sorry, I don't need that. 2.5. Okay, times 15 meters. Okay, all right, so my final velocity is 8.66. So 1/2 times 1.02 kilograms times 8.6 squared. So there's my mass times my speed squared. Whoop, I put divide. Hang on, I'm back and fix that. Look at that. It's pretty much the same number, 38 joules. Okay. So does it matter which way I do it? Okay. With work energy theorem, there's often more than one way. This time, it just so happened they were about the same amount of work. Okay. In most work energy theorem questions, this method's a little more work, because usually you have to find the net force with sum of all forces first, and that takes longer. Okay. In this case, because it was simple, we were just able to go mass times acceleration and we had it. Okay. But either way, we'll get you the same answer. Okay. It's kind of the point of that question. Everybody all right with that? All right, this one is going to lead us into what we're going to talk about tomorrow. Okay? So I drop an 8-kilogram object from a height of 7 meters. What is the kinetic energy of the object as it hits the ground? If I drop something, what's the only force acting? Okay, so that means I convert all of my potential energy into what? Right, I don't lose any from top to bottom. Does that mean energy is conserved? Yes. Okay, it means that in this case, my initial mechanical energy equals my final mechanical energy. Okay, so all I have to do is find my initial potential energy, because all my energy is potential since I'm dropping it. That will equal my final kinetic energy, because all of it has to be converted. None of it is being lost to anything on the way down. Does that ring a bell from last year? Right? We did those roller coaster questions last year. They all started like this. My initial energy equals my final energy because energy is conserved. That's different than a work energy theorem problem where we go EF minus EI because they're different. Okay? In a conservation of energy question, they're the same. So all I have to do is go 8 times 9.81 times 7, okay? And that's going to be 550, or 5.5 times 10 to the 2 joules. Okay? That's a great multiple choice question. Okay? So is the one with the 2 cannonballs. 2 cannonballs is also a great multiple choice question. Okay? Because you don't actually have to calculate anything to get the right answer for that one. Or you can do all the calculating and get the right answer, and that way it's nice. Okay, because you can get the right answer whether you know how to do math really well or whether you just understand physics really well. And both ways deserve to get the right answer. So in that way, it's a great multiple choice question. All right, so that's going to lead us to this. This is what you would have done last year in Science 10. There's a kid sledding down a hill. Okay? The kid and his sled start 25 meters above the bottom of the hill vertically. Okay? Moving at 3.1 meters per second. A little while later, or further down the hill, okay, the speed of the kid and his sled is 9.6 meters per second. How far above the bottom are they at that point? The hill is frictionless. So no energy is being lost and no work is being done between the starting point and the ending point in this question. What does that mean for your mechanical energy, top versus bottom? They're the same. Okay, see what you remember from Science 10. This question starts out with the law of conservation of energy. My initial mechanical energy and my final mechanical energy are equal. You need to solve for the height at the second point. Okay, so initially, I have both kinetic and potential energy. Would you agree? Okay, so if I'm writing this here, I've got potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Okay, what I'm looking for is part of that term. Agreed? Okay, so I'm going to subtract this term over before I put in all the other variables. Is that okay? Okay, so I'm going to have EP initial plus EK initial minus EK final equals EP final. That's going to mean M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals MGH final. Everyone okay with that?
Yes.
What am I not given?
Maths.
Does it matter? No, it's in every term. Okay? Doesn't make any difference, so I can cancel it. All right, all I want is HF. What do I do with G? Divide both sides by G. All right, plug in my numbers and solve. Ends up being 20 point something. Okay? So 25 times 9.81 plus 0.5 times 3.1 squared minus 0.5 times 9.6 squared divided by 9.81. 20.8. Okay? All right, that's what we're going to be working on tomorrow after your quiz on work energy theorem.
Mr. Coderre,
Yeah.
can I interest you in